Okay, I think we can start the second part now. We'll talk about some of the primitives of quantum computation. These primitives are important constructs if you want to build a quantum circuit that corresponds to a certain quantum algorithm. And one of the most important of these primitives is what we call Fourier sampling. Uh, Fourier sampling is basically an Hadamard gate tensored n times. In other words, you have an n qubit system and you apply a Hadamard gate to each one of these qubits that produces a superposition and an entangled state. This is very commonly, we are going to see this construct in almost all of the quantum algorithms that we are going to discuss. So it's important, to understand, how it works. Let's start with a single qubit and a single Hadamard gate. Uh, okay. As we have seen, the unitary transform for this kind of a gate would be 1 over square root of 2, 1 over square root of 2, 1 over square root of 2 minus 1 over square root of 2. And this single qubit gate, it transforms a cat 0 state to a cat plus state, which was 1 over square root of 2, cat 0 plus cat 1. And it would transfer a cat 1 state to a cat minus state, which was 1 over square root of 2, cat 0 minus cat 1, right? And let's suppose we add another qubit now. We have a 2 qubit system. So this, this is Hadamard tensored twice on this 2 qubit system. So this would transfer a cat 00 state, right, to cat plus plus state, because each one of these Hadamard gates would transfer the corresponding qubit cat 0 to a cat plus state. And if you compute this, this is cat plus tensored with cat plus. In other words, 1 over 2 cat 0 plus cat 1 tensored with cat 0 plus cat 1, right? As we have seen before, you'd obtain an equal superposition of all the basis states, right? 1 over 2 cat 0 0 plus cat 0 1 plus cat 1 0 plus cat 1 1. This is an equal superposition of all the cat ij available basis states. Similarly, in the input, instead of cat 0 0, we can start try the other combinations like cat 0 cat 1 cat 1 cat 0 or cat 1 cat 1 in the input. You'd always get eventually a linear superposition of all the basis states, cat 0 0 cat 0 1 cat 1 0 cat 1 1. But the only difference would be the plus and minus signs, in front, these phases in front. So in the case you have, for instance, cat 1 1 in the input, right? And if you apply this Hadamard operator, Hadamard tensored 2 time operator on the cat 0 0 state, right? Each one of these would be converted to minus state, cat minus and cat minus. And equivalently, if you multiply this out, you would find out that we have 1 over 2 cat 0 0 minus 1 over 2 cat 0 1 minus 1 over 2 cat 1 0 plus 1 over 2 cat 1 1. So all computational bases that are input states, they are converted to linear superposition of these bases of 2 to the n bases with amplitudes plus and minus 1. And in all these cases, regardless of the number of n, you could increase the number of qubits indefinitely, basically. You'd always have this linear superposition with plus and minus phases. And always the number of plus phases would equal the number of minus phases, right? In matrix form, right, this H tensor twice, you could represent this in matrix form, right? This is H, tensored with H. We have seen this in the class, but it's, I think, important or useful to remember. This kind of a tensor product would be you multiply each one of the elements of the first matrix with the second matrix. So this is 1 over square root of 2h, 1 over square root of 2h, 1 over square root of 2h minus 1 over square root of 2h. In other words, if you put this in a matrix form, right? Since it is a 2-qubit system, we have to have a 4 by 4 matrix, right? This is the matrix we have. In other words, this matrix is equivalent to this Hadamard tensored twice, circuit. And as you see, all of these columns or equivalently these rows, right? They have plus and minus, of the phases that corresponds to the plus and minus phases in front of these basis states. Okay, so let's increase one more. Let's go to n equals 3 qubits, right? In the input, we have cat 0, cat 0, cat 0, and then we applied Hadamard to each one of them. So each one of them is converted to a plus gate, cat plus, cat plus, cat plus. So this would produce a linear superposition of all the 8 basis states that we would construct 3-bit strings, of zeros and ones. So this is a summation over all the basis states, all possible bases, cat 0, 0, 0, cat 0, 0, 1, cat 0, 1, 0, cat 0, 0, 1, 1, cat 1, 0, 0, cat 1, 0, 1, and cat 1, 1, 1. And again, if you tried other inputs instead of 0, 0, 0, you would obtain states, linear superposition of the states, but the only difference would be the phases, the signs in the front. They would be plus or minus, depending on how many, when you multiply it out, how many pluses, how many minuses, there are, how many minus states there are, in the equation. So in general, for the n-qubit case, right, we can easily extrapolate this. In the input, we have n qubits of cat 0, and we applied Hadamard, tensored n times. In other words, Hadamard to each one of them. So you have plus states for each one of these zero states in the input. Equivalently, we can express this as 1 over square root of 2 cat 0 plus cat 1. This is a plus state, tensored n times, right? This is the output. So you tensor, n times cat plus to obtain the final quantum state in the output. And if you multiply this out, this is nothing but linear superposition of all the cat x basis states. Again, as the x is all the combinations of zeros and ones of length n string. So you obtain a linear superposition. This is 1 over 2 to the n over 2 is just a normalization factor. Since you have 2 to the n such basis states, right? The sum of the squares of all these magnitudes should add up to 1. So this is what it does. This is just a normalization factor in the front. And in general, an Hadamard transform on an n-qubit system results in the superposition of the Hadamard tensored n basis states. But for a general input, right, one can actually easily, verify that this is the transformation we have. So this transformation now considers all possible cat u input states, cat u1 up to u sub n. So not necessarily only a cat 0 state, but any combination, of zeros and ones of length n. So this would you'd end up with this. This is, in other words, if we apply on cat u a generic input state, the Hadamard gate, tensored n times, one Hadamard for each one of the qubits, you would obtain, in general, again, a linear superposition of all the cat x, all the possible values of basis and with strings of zeros and one. But in the front, you have this phase. This is just a phase. It is either a plus one or a minus one, right? And this, whether it is a plus one or a minus one, depends on what u is, right? It is minus one to the u dot x. Again, this is just a normalization constant, but this minus one to the u dot x determines the phase. It's an inner product. U dot x, it's either a one or a zero, right? If u dot x, in other words, in mode 2 sum, inner product mode 2, because u dot x, as we see over here, x is one of the basis states, which could be represented as x1 plus x1, x2 up to xn, and then u is the input vector, which could be represented as u1, u2, dot 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 u sub n. U dot x is just the inner product between the input and all the and this corresponding basis state, right? So this and this is a modulo 2 sum. So this is either a 0 or a 1, right? Like for instance, let's consider the case when we have the input cat 0. All the qubits are in the 0 state initially. So in this case, minus 1 to the u dot x, right, would be 0 because the input state is 0. All the elements of u is 0. u1, u2, u3 up to u sub n, all of them are 0. So no matter what x you have, right, in this summation, you end up with a 0. So minus 1 to the 0th power would be 1. So this actually verifies, that our previous derivation over here, that if in the input we have u equals 0, right, all these phases, these coefficients, they are all 1. So this reverts back, to this formula over here. So there's nothing, unusual about this. This is u dot x. It's either a 0 or a 1. If it's a 0, this phase becomes minus 1 to the 0, which is 1. If it is a 1, it becomes a minus phase. So again, this produces a linear superposition of all the possible cat x states with in the front with phases either plus or a minus, depending on what the u input vector is. Okay. Okay. So I'd like you to convince yourself that these phases that we introduced over here, minus 1 to the u dot x, they are actually they correspond to the actual phases. In other words, if you have a generic u vector in the input, u1, u2 up to u sub n, right, consisting of a random combination of zeros and ones, this operation, Hadamard tensored n times operating on u, actually corresponds to this, with this phase. Convince yourself. It's important, because we'll use this construct over and over again. It's important to understand and know by heart, that how this construct works. So the title of this primitive was, the name for this primitive was Fourier sampling. And Fourier sampling is when we make a measurement in the output, right? This is called the Fourier sampling primitive. In the input, you have a generic cat psi state, and you apply Hadamard tensor n times, and in the output you have another cat psi hat or cat psi prime with different beta sub x coefficients. In the output, we make a measurement. But when we make a measurement, we measure one of these eigenstates, as usual, according to the measurement postulates, right? With probability beta sub x square, we measure one of the output values, one of the possible output states out of 2 to the n n states. One of these y's with the given with this magnitude squared probability. So this construct is called Fourier sampling. When we discuss other more advanced quantum algorithms like quantum Fourier transform and others, we'll use this construct pretty often. I mean, at this point, it's not very obvious why is it called Fourier sampling. It's just you have a generic quantum state in the input. You apply an Hadamard tensor, n times, and in the output you have another transformed quantum state, and you sample. In other words, you measure, this quantum state, and that means you sample, this quantum state. In other words, you measure one of these 2 to the n quantum eigenstates. So this construct is referred to as the Fourier sampling primitive. Okay, now I continue. Another important quantum computation primitive is what we call bit and phase oracles. An oracle is basically another name for oracle. It's a black box. It's a quantum circuit that we can query. In other words, we query, an oracle is something like this. And we don't necessarily know what the circuit is, but it's just a unitary circuit, right? A quantum circuit that we query. In other words, we apply an input and we get an output f of x. This is called an oracle, and in some texts, it is referred to as a black box. And it's going to be an important primitive that we are going to study of the quantum algorithms. And as we said, in general, we do not necessarily need to know the detailed construction, gate construction of an oracle. We might, we might build the circuit, but we don't necessarily have to know. And we'll see, as we go along how this is applied. And as we said, a quantum circuit must be reversible, right? In other words, in a function or a mapping, right, from a string of n bits in the input to a string of another n bits in the output. So this kind of a mapping, in order for it to be quantum mechanically constructible, it has to be reversible. That's what it means, to be a unitary operator. That's just another name. And as we have discussed, it is possible to convert any classical function, f of x, right, to a reversible form using this following construct, right? Let's suppose we have a unitary transform u sub f, and that computes f of x on cat x input, right? Just by introducing an ancilla bit, or this could be a string also of cat y, right? In the output, again, we produce cat x, the same as the input, but we also generate the function f of x that u sub f computes in this form, cat y modulo 2 sum or exclusive or f of x, right? I mean, if you, I mean, it's easy to see. If y equals 0, for instance, right, this output would be f of x, because 0 plus f of x modulo 2 would be f of x, always. So this kind of a construct, it's called a bit oracle. It's a black box, model. So in the input, we have cat x tensored cat y, right? This is our input. And in the output, we have cat x tensored y plus f of x, modulo 2. So this is called a bit oracle. And we have already seen, this kind of a construct like a CNOT gate, right, can be considered as a bit oracle because in the input we have cat x, cat y, and then in the output we have cat x and cat x plus y, right? I mean, for f of x equals x, for this form of f of x, CNOT can be considered actually as a bit oracle, right? So this bit oracle enables us to convert any classical f of x, classical function, to be represented as a unitary reversible circuit, like this. So we can formally now define a bit oracle. If in the input we have cat x and cat y, cat y being the ancilla bits, and we apply a unitary transform u sub f, a function. In the output, we have cat x, cat y plus f of x. This kind of a unitary transform is called formally a bit oracle. Sometimes it's called an XOR oracle because this modulo 2 sum is the same as an XOR operation. And you also notice, that for y equals 0, right? 0 plus f of x is f of x. If in the ancilla bit, if we set it to be 0, we can obtain f of x in the output. There is another kind of oracle, another kind of black box circuit model. The only difference now and it's called a phase oracle. The only difference between a bit oracle and a phase oracle is that the ancilla bit, the cat y ancilla bit is in minus state, cat minus state. So in this case, this kind of an oracle is referred to as a phase oracle, and we'll see why. It is important because we are going to see, that this in the ancilla using cat minus state brings this output f of x as a phase, as a phase in the output. And as we discussed, the whole logic, between in developing a quantum circuit, quantum algorithm is to adjust, the phases such that the desired cat in the output is enhanced. It constructively interfere. So it has benefits, important benefits to bring this cat of x to a phase, in the form of an exponent that we'll see, right now. So the only difference between a phase oracle and a bit oracle, as we said, in the input as a cat y, ancilla bit, we have the cat minus state, and this primitive is called a phase oracle. The use to understand the use of phase oracle, and by the way, phase oracle and bit oracle, they are interchangeable. I mean, they are equivalent, but just different representations. A bit oracle, using a bit oracle, you can construct any classical f of x function in the form of an invertible or a reversible unitary u sub f. And in this kind of a construct, when ancilla bit is cat minus state, then you can do other tricks, to build quantum algorithms. And to understand how it works, just let's compute, the output when the input is cat minus, the ancilla bit is cat minus. Let's compute the output. Again, let's remember, this function is n-bit string, a mapping from n-bit strings to a single bit string. So in other words, f of x is either 0 or a 1, right? So in the input, we have the cat x tensored with cat minus, right? This is cat x, cat minus in the input. And we apply the unitary U sub f to this, and in the output we obtain cat x, right, tensored with cat minus plus cat f of x, right? This is my output state. And if we compute this, what this actually does is this is cat x, and I write the minus state in the standard basis at cat 0 minus cat 1, modulo 2 sum cat f of x. And if you multiply this out, again keeping the input state cat x outside, we have cat x 1 over 2 square root of 2 cat 0 exclusive or f of cat f of x minus cat 1 exclusive or cat f of x. So this again f of x can have two values, right? F of x can be 0 or 1 because this is a mapping from n bit string to a single bit string. So if f of x equals 0, right, over here f of x is 0, this is just cat 0 minus cat 1, right? This equation over here. So if f of x is 0, we have 1 over square root of 2 in the output as cat 0 and cat 1, right? This is just a cat minus state. So if the circuit happens to compute f of x to be 0, then in the output we have cat minus state. On the other hand, if f of x equals 1, right, if you plug in f of x equals 1 over here, and cat 0 plus cat 1 is 1, and this is minus cat 1 plus cat 1, this is so this sum becomes cat 0. So the output becomes 1 over square root of 2 cat 1 minus cat 0, which is nothing but minus cat 1, minus cat minus. And one way to represent this is this state is cat x minus 1 to the f of x cat minus, right? Why? Because if f of x is 0, you have minus 1 to the 0, and this phase becomes 1. If f of x is 1, this phase becomes minus 1 to the 1, which is minus 1. So this, and we can minus 1 to the f of x, we can bring this out because this is just a multiplication factor. This is just a phase. This value, remember it's either a 0 or a 1. So we can take it out, of this tensor product. So this entire output now of the bit oracle becomes minus 1 to the f of x cat minus, right? What we have done is the f of x information, the value of f of x that we had in the output, now we have brought it up as an exponent, f of x, right? So to summarize, in the input, this is a phase oracle. In the input, we have cat x and cat minus as the ancilla bit. In the output, we computed minus 1 to the f of x cat x, and the ancilla bit, remains cat minus. So in this kind of a representation in the phase oracle, now the value of the function f of x, if you look at it, right, it determines the phase in the output of the input basis. It determines how the phase of cat x is transformed as a result of this unitary transformation. And it's we'll say it's going to be very useful to design algorithms, and these algorithms, as we said, we want to the phases to add constructively to obtain the desired solution. So it will be very useful to have this the value of the function comes as a phase of this cat x state. Well, it may be a little confusing, without seeing an actual implementation. But this again will be these two oracles, black box models of bit oracle and a phase oracle will be very important constructs in many of the algorithms that we are going to discuss. And it's also, again, just like the Fourier sampling primitive, it's very important to understand the how the bit oracle and phase oracle primitives work. Just to illustrate, just to make it more concrete, what kind of constructs these oracle boxes, black boxes, could be. This could be a string of zeros and ones, for instance. And in the oracle, inside the oracle, the circuit could represent a cat u, state of cat u1 to u sub n. Right? This could be a string, or in this case, the currying means to look up a value of the string, of u sub k. So when we query, that kind of a black box, we would obtain one of the values of u sub k, of the cat u that is that this unitary transform represents. Or alternatively, an oracle could be any other function that we query, right? Any mapping, end-to-end mapping, from n bit n bit strings to n bit strings. This could be any function, like this, or any mapping like this.